Sequences can be thought of as an ordered list of numbers. Here are a couple of examples. Now in this one, notice that the dot 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 appears here at the end of this group of numbers, and it just means that we're continuing on forevermore. So this then would represent an infinite sequence. Sequences can either be infinite or finite. Here's another example of a sequence. Notice the sign change from item to item here. That's one characteristic that appears in sequences. Now a notation for designating an item within this list would be to use a little subscript notation like this. A subscript 3 means the third item you see in a sequence. So A sub 3 for this sequence would be 6. Now another arrangement similar to this is where the listing of items A subscript some number starts at 0 rather than 1. It's a little unusual, doesn't happen all the time. We'll call attention to it when it occurs. But mostly we'll be concerned with this kind of arrangement. Now the items within a sequence can be generated in a number of ways. We can kind of have a listing like we saw here before and continue with that listing if we see the pattern. But a lot of times the pattern is given as an expression. For example, this notation is often used. A subscript n means the nth term is generated by using this expression. Right? And it just means that we're going to apply the number 1 here in place of n, and 2 and 3 and 4 and so forth. So A subscript 1 would be 2 times 1 minus 3, which would be negative 1. A subscript 2, just replace the n with 2 and evaluate, and we get 1. So we have negative 1, 1. A sub 3 turns out to be 3. A sub 4 turns out to be 5. And then in this way, we can generate whatever term we'd like to. If we want to generate the 10th term, you see A subscript 10, it would be 2 times 10 minus 3, which is 17. Now, another notation again for this, I want to have a look at these items within the sequence. You know, if we were listing the items, we would list them with this negative 1 first. So it would be negative 1, 1, 3, 5, and sometimes in this ordering and listing of the items in a sequence, the expression for generating terms is also listed, kind of like this. You list the first several items in the sequence, put a comma, and then put the expression generating the items within the sequence, and then another dot, dot, dot. It's just another way of saying pretty much the same thing we have here. Here's another sequence. The interesting thing about this one is that the counting mechanism n is an exponent on negative 1, and that will serve to change the sign of this term. Let's see what happens. A sub 1 means replace the n with 1. So all these other items stay the same. But we have 1 as the exponent on negative 1, so we have negative 1 times 2, or negative 2. 3 with negative 2 is 1. All right? When n becomes even, you see when n becomes 2 here, squaring the negative 1 makes this positive 1. So this is 3 plus 2, 5. When we go to an odd value for the exponent on negative 1, this is negative 1, so we have negative 2 for this term. 3 with negative 2, 1. And then back to an even exponent makes this plus 1, so 3 plus 2, 5. Now notice this just swapping back and forth from one item to another. 1, 5, 1, 5, 1, 5, 1, 5, and so on. A peculiar kind of arrangement for sure. In some circumstances, we need to actually generate the expression that is associated with a certain sequence. Now this may be the toughest thing to do in this whole study of sequences because it's not always abundantly obvious what has to be done. But here's how you begin the thought process. You take a look at the items in a sequence, and our goal here is to write an expression that will generate these items. Now that expression will contain n, or k, or some counting mechanism, and that counting mechanism we'll think will start at 1. Now it could start at 0, but let's consider it to start at 1. So we want to associate the number 1, 2, 3, 4, 5 with the items within the sequence. Now sometimes it's pretty easy to see a relationship there. I mean the relationship is fairly obvious here, I think, because each of these items each of these n's are squared to give the numbers within the sequence. So we could simply say then that the nth term is generated by taking in the counting mechanism and squaring it. 1 squared is 1, 2 squared is 4, 3 squared is 9, and so on. But have a look at this one. We have, let's see, 2, 5, 10, 17, 26, and we want to associate those with 1, 2, 3, 4, 5, and so forth. You see, it kind of gets a little more complicated very quickly here when we see stuff like this. And a lot of times you have to analyze this in a lot of different ways. Now for this one though, it's not too terribly difficult because we might see that the numbers that are listed here are related to the numbers that are up here. They're just one larger than these. So we could then say that the nth item, a sub n, is simply those n squares up there plus 1. So here's the expression that generates these items. Now, another situation that occurs from time to time is where we have an alternating sign situation. Suppose up here, for example, I just make this -4, -16, and then the next item would be negative, and so we have the alternating sign notion. Well, when an alternating sign pattern occurs within a sequence like this, and you can pretty well bet that we're going to have -1 to an exponent which corresponds with the counting mechanism in some way. Now in this one we want to do this kind of thing. I'm going to just slide the n squared over here because we still want n squared for the numerical part without regard to sign. So I'm going to put the n squared over here. Now we want a -1 to some exponent, and the trick is to identify the exponent. Now if I just make -1 to the n power, then when n is 1, we would have -1 to the 1 power, that's -1 times 1 squared, you see, which would be -1. Oh no, we want this to be positive. So we want an even exponent, you see, on that first item. How do we accomplish that? Well, we just make this exponent n plus 1. I'm going to make this a little bigger for emphasis here. Make this n plus 1, you see, and in fact I want to slide this over too for emphasis. So it's kind of like this. So for the first item we have 1 plus 1, 2 as the exponent on -1, making it positive. And this is 1 squared for 1. And then for the next item, when n is 2, we have 2 plus 1, 3. And an odd exponent on -1 makes it negative. And so 2 squared is 4. That makes it -4, and all is right. So there's just a lot of fishing around that goes on with this, this kind of process sometimes. A notation that is associated with sequences quite often is called factorial notation, and it can be thought of as simply an operation symbol. Factorial notation is indicated with an exclamation point, and I can define it most easily by showing an example. 5 factorial is equal to 1 times 2 times 3 times 4 times 5. So we're beginning with a factor of 1, and we're multiplying times integer values all the way up to the number indicated here. Now the 1 is not going to play a big role in changing the value here, so it could be left out, and often we'll leave it out. But just for emphasis, technically it begins at 1 and goes all the way up to the number indicated here. Now another way to list the factors, of course, is in the reverse order, and a lot of times when we use factorial notation, this is a handy way to do it because of cancellation opportunities that we'll see very shortly. Okay, then the idea is to multiply the factors and get some kind of result. Now factorial numbers, when you take the factorial of a number, the value of that number to the factorial idea gets really, really big, really, really fast. In fact, you might use your calculator and make the calculation of factorial. And I forget at the moment where the factorial symbol is on the calculator. Maybe I'll tell you that later. It's probably in the math menu under number or something like that. But something like 80 factorial, which seems to be a relatively small number, I believe has to be listed in scientific notation by the calculator because you run out of digits pretty quickly when you talk about such huge numbers. At any rate, let's talk about some other aspects of factorial. As a special definition, 0 factorial is defined to be 1. Now here's a technique that's often used when factorials are involved in problems. If we have 12 factorial over 10 factorial, you know, this is just a string of factors, 12 times 11 times 10 times 9, all the way down to 1. And this is a string of factors. It's 10 times 9 times 8 times 7 and so on. And we could list all of those factors for numerator and denominator and take a look at the cancellation opportunities. But we can see them a little more efficiently, I think, like this. We can rewrite 12 as 12 times 11 times 10 factorial. And I'm stopping right there because I notice that the denominator is 10 factorial, and I'll just bring it over. Now, this indicates a bunch of factors, and that indicates a bunch of factors, and they're all the same. So I can cancel these two, you see, without listing all of the separate factors. And now I have just 12 times 11 to evaluate here for the value of this expression. In a similar way, we can perform a cancellation or simplify when letters are involved. N plus 2 factorial over n factorial can be simplified like this. Now I'm going to come down. The n plus 2 factorial means we're taking the term n plus 2 and then multiplying times, let's see, one less than that would be n plus 2 minus 1, or simply n plus 1. And then one less than that means n plus 1 minus 1, and that's simply n. So this is n, I'll list it as n factorial because in the denominator I have this n factorial, and I know that all of these factors involved with this cancel with all of these factors. They're gone, and so my expression becomes simply n plus 2 times n plus 1. And that's all there is to it. Another notation used in the study of sequences is summation notation. Now, summation notation is also referred to often as sigma notation because it uses the uppercase Greek letter sigma. So sigma meaning sum now in the mathematical sense. Now, here's how sigma notation works. We have this Greek letter sigma, and at the bottom we have a letter set equal to a number. And that letter appears in an expression over here. Now, we also have a number at the top of the Greek letter sigma. This is called the index of the summation. This is the lower limit, and that's the upper limit of the summation. And we're just adding a bunch of things. And the things that we are added are generated by using this expression and replacing k with all of the values from this lower limit to the upper limit. You see, so this means we're adding this expression when k is replaced with 1, and plus this expression when k is replaced with 2, plus this expression when k is replaced with the upper limit 3. You see, this is a rather narrow group of things being added, but nonetheless, that's the idea. So to expand this, we would take this expression and replace the letter in it with the lower limit value, and then replace that index with every value up to the upper limit. So it would be 2 times 1 plus 1, plus 2 times 2 plus 1, plus 2 times 3 plus 1, and then we would evaluate to find that to be 15. Now when items in a sequence are added, the situation is called a series. And a series can be either infinite or finite. That is, we can be adding an infinite number of numbers, or we can be adding a finite number of numbers. Here we're adding a finite number of numbers, and so it's called an nth partial sum. An nth partial sum. Okay, let's take a look at a couple of other situations. Here we have, let's see now, the counting mechanism here, the index is n rather than k, and it can be pretty much any letter that you'd like to assign to it. The lower limit is 1, once again, and this lower limit can change. It can be almost anything that you want it to be. It could be 5, and then we could go to 10 or whatever. So it can be all over the board. But at any rate, the lower limit is 1, the upper limit is 3, just as was the case in the previous problem. The expression is 4n, so n is taking on values from 1 to 3. So we have 4 times 1 plus 4 times 2 plus 4 times 3. And evaluating, we find that sum to be 24. Now, one of the properties involved in this kind of notation is this. You may notice that 4 is a factor in all three of these terms. And it does turn out that because of this, the nature of this expression, that 4 can be written over here. That is, we can take the 4 and write it as a coefficient of this summation notation. You see, we can just kind of alter it like this, and we get the same result, because this means we're going to add as n takes on values from 1 to 3. So it's 4 times, now this part is 1 plus 2 plus 3. So it's 4 times 1 plus 2 plus 3, or 24 as expected. Now another Another property has to do with the notion that summation notation, or this summation idea, can be distributive, or it is distributive in nature. Let me show you an example of that. Come back over here and let's look at this first problem. I could actually rewrite this like this. I could say, well, the summation of items given by this expression can be thought of as the sum of this rascal plus the sum of that. That is, it's the sum as k runs from 1 to 3 of 2k plus the sum as k runs from 1 to 3 of 1. And this could further be manipulated a bit. It really isn't necessary in this context because the problem is pretty simple, but in other situations this is going to be a pretty valuable tool. The 2 can become the coefficient here, so we could write this as 2 times the summation as k runs from 1 to 3 of k, and then plus the sum as k runs from 1 to 3 of 1, and evaluate these separately. Now, this, you know, we just saw an example of this situation where k takes on the value 1, 2, and 3. So we'll have, this will be 2 times, and then 1 plus 2 plus 3. And we haven't seen this situation yet. We're going to talk about it a little more over there. But to brief you on this, it's this idea that what is the value of this expression when k is 1? You see, the expression has no k in it. It won't change value at all. As k changes value, the expression here won't change value because there's no k in it. So when k is 1, this expression is 1. When k is 2, the expression is 1. When k is 3, the expression is 1. Well, at any rate, adding here, we get the same result that we did before. All right, here's another situation. Now, in this one, the counting mechanism is starting at 0, and it goes to 3. And the counting mechanism is part of an exponent. It is the exponent on 2. So we would have, let's see, now, so 2 to k as k goes from 0 to 3. So it'd be 2 to the 0 plus 2 to the 1 plus 2 squared plus 2 cubed. And then evaluating, we find the value to be 15. I want you to notice here that when k takes on a value other than 1 as the lower limit, that the upper limit doesn't tell us the number of items in this group that we're adding. And let me say it another way. It is often thought that when we use this summation notation, that the upper limit indicates how many items are being collected here. And that's true if that lower limit is 1. For example, if we're going from 1 to 5 with this counting mechanism, then we have 5 items to be added. Sometimes that's a valuable thing to know. How many items are in this series? How many sequence items are being added? That's another way to say it. Okay, so when we have 0 involved, then it kind of adds 1 to the list of items being added. We have really 4 items and not the upper index here. Okay, here's that situation with a constant again. And it's the notion that k is running from 1 to 4, but k doesn't actually appear here in the expression. So when k is 1, the value of the expression is 3. When k is 2, it's still 3. When k is 3, it's still 3. And when k is 4, it is 3. Now, notice here that in this circumstance, we have 1, 2, 3, 4 threes. So really, we could have just said that this is 4 times 3, or 12. And it turns out that when you're starting with 1 and you're going to 4, I mean, all we have is this constant, the number of times, you see the number of items that we have that's being added. If we can understand that we have 4 items being added, it's 4 times 3, as we have here. And that's one of the values of knowing how many items we have according to the lower and upper limit numbers. Here's another situation where k begins at 0, and this time the upper limit is 8. And the expression is 1 over k factorial. Now notice factorial comes into play here for the first time in this summation notation. So let's see. Well, all we want to do when you first start to evaluate these is just just write what this means. Just expand it a little bit. Kind of replace the letter with numbers. That's all you want to do. And then evaluate each separate item that's being added. It's kind of important to do it that way because these problems can have a lot of different looks. They can look very different from one another, so don't make any assumptions. Just kind of go with your basic conceptual understanding of what this means and expand it, and then start to evaluate. Okay, let's see. 0 factorial is 1, so 1 over 1 is 1. 1 factorial is also 1. 1 over 1 is 1. This is 1 over 2 factorial, which is 1/2, and so on. When we get out to 1 over 8 factorial, it's 1 over 40,320. Now, adding all of these fractions, adding the fractions out here with the 1 and the 1, it turns out that the value is approximately 2.71828. Now, this may look vaguely familiar to you, or it should look a little familiar to you. This is the approximate value of the naturally occurring constant E that we studied in a previous chapter. And this is an interesting way for E to sort of make its appearance in another area of our study. Now, it does turn out here that if we had more items being added in this series, that is, as this number grows larger and larger and larger, the value that for the expression is closer and closer and closer to E. And as a matter of fact, if we said we're going to add an infinite number of items, then the value here would be exactly E. Let me show you another situation with this same theme. If n runs from 0 to infinity, now then we have 1 over 2 to the n power. Then n starts at 0 and goes to infinity. So I can indicate it like this: 1 over 2 to the 0, 1 over 2 to the 1, plus 1 over 2 to squared, plus, and then ... Means it goes on forever. Okay. Now, beginning to evaluate, this becomes, let's see, 1, 1/2, 1/4, 1/8, 1/16, 1 over 32, and so on. It turns out that adding all of these, or this indicates then that the expression becomes exactly 2. Exactly 2. Let me point out one other thing here before I leave this board. This ... this is a notation that I used up here and I didn't really call attention to it, but when we kind of have a break in the action and we don't want to list all of the ... in a finite list, this is a finite list, that's an infinite list, but we can list some of the items in this list and use a ... to say there are some items between these two. So we list a few items and then plus, and then ... and then plus the last item, and we understand that we're listing all of the items that are indicated with our notation.